Yeah, good morning. Let me now go into the optimization exercise and try to resolve some of these problems. Now, this problem was more or less similar to the one that we were able to handle with respect to the previous example. We have minimized the sum of the two reactor volumes in order to get a particular conversion. Though the problem statement is slightly different, I think you will be able to handle this problem as it is. Now you can see the reactors are operating, four reactors are operating in series. The reaction is being conducted in them. It is given as half order with appropriate kinetics. The sum of the four reactor volumes must be equal to 20 meter cube, but the reactors need not have the same volume. So you are required to maximize the exit conversion for an inlet volumetric flow rate, right? So you may be able to vary the volumes such that the conversion is maximized at the exit. Now let us go ahead with this problem. Yeah. Now once again we are going to handle the same components: ethylene diacetate, then acetic acid, then methyl acrylate, right? Say next. Let me once again choose Chavo-Seder method. Say next. Go to simulation environment. Sorry. Setup. Yeah, we have four CSTRs now connected in series. Now let us connect the input and output streams. Say next. So temperature is 750 Kelvin. Pressure is 1 atmosphere. The total flow rate in terms of volume is 71 meter cube per hour. Cubic meters per hour. Say now this is with respect to the block. We have specified the input stream. Now the block is operating at 1 atmosphere, 750 Kelvin. Let me assume the volumes as 5 cubic meters. So let me also create the reaction. Again, a power law model. So it was given that it is half order rate with respect to ethylene diacetate, acetic acid 1, methyl acrylate 1. Now let us specify the kinetic information. K is 7.8 E9 and the value of E is 38,200 calories per mole. Say next. So this is the reaction that is being conducted. Say next. We have specified block 1. Now similarly, you need to specify all the other blocks, all the other 3 reactors. 1 atmosphere, 750 Kelvin, let us say 5 cubic meters. Say next. So same reaction is being handled. So B2 is specified. Similarly, B3, 1 atmosphere, 750 Kelvin, 5 cubic meters. Next, R1, next, 1 atmosphere, 750 Kelvin, 5 cubic meters. Say next. Now let me also use the optimization toolbox straight away. Say new, okay, variable. What is that our objective? Conversion. Now it's a stream variable. Again, we wanted to maximize the conversion. What does that mean? We wanted to minimize the flow of ethylene diacetate at the exit of all the 4 reactors. Right? Say next. So I wanted to minimize conversion. Right? Do I have any constraints? I have one constraint, that the sum of the total volumes must be 20. So we need to define all those reactor volumes. V1, it's a block variable. Block is B1. Variable is volume. This is in cubic meters. Right. Similarly, next V2. Again, it's a block variable. Block is B2. Variable is volume. Again, cubic meters. Next V3. It's also a block variable. Block is B3. Variable is volume. Again, cubic meters. Next V4. This is the volume of the 4th block. Again, cubic meters. Say next. So spec is V1 plus V2 plus V3 plus V4 should be equal to 20 meter cube. Let us allow some tolerance. Next. Sorry. So this constraint should be made effective. Say next. What is that we are trying to vary? So we would like to vary all the 4 reactor volumes. B1 volume. So you can say some lower limit 0.1 to about 10. Say next new. Similarly, block variable, block is B2, variable is volume. This should be in cubic meters. This also should be in cubic meters. Again 0.1 to 10. New block variable, block is B3, volume in cubic meters, say 0.1 to 10. New block variable, block is B4, volume, this also must be in cubic meters, 0.1 to 10. Next. So what is that we are trying to do? We are trying to vary the volumes of all 4 reactors such that the exit conversion is maximized. And what is the conversion? What is the constraint that we have? The only constraint that we have is the sum of the 2 reactor volumes must be 20 cubic meters. But for that, there is no other constraint. Yeah, we were able to come to a convergent solution within 7 iterations. Again, the method that has been used is sequential quadratic programming. Let us look at the stream summary. So ethylidene diestate is entering at 519.568 kilomoles per hour, and we were able to reduce it to about 190.268 kilomoles per hour. Now you can also see the results here. Yeah, so we were able to come to this solution. And what about the constraints? So we got the volumes as 5 cubic meters, right? Thank you.